Welcome to the second lecture of this master course, Renewables and Electricity Markets. Today we are going to talk about fundamentals of electricity markets. Before that, a few announcements, but you already saw maybe those announcements on DTU Alert. First is that assignment 1 has been released, so you can check it on DTU Alert. Also, I uploaded a good sample report from the same course 2 years ago. So it's a good report that you can see what you are expected. Also, I uploaded a rubric table with, breaking down grades, how your report will be graded. That's the first announcement. Second, I just posted on DTU Learn. So to make a Kahoot quiz a bit more interesting for you, so and also make sure that you will listen carefully during the lecture, I offer 1% extra to your final grade. I mean, after the average. So let's say the average you got 92. Now with this 1% extra, the final grade will be 93%. And it will be offered only to top score. So it could be a group, individual person or a group of 2. If it's a group of 2, this 1% will be offered to both of them, 1% each. Yeah, so I hope this makes Kahoot quiz more interesting to you. And for people online, I'm checking my Zoom chat box constantly. So if you have any questions, so please feel free to write your questions in the chat box. I'll answer right away. And please keep muted. Good. So, fundamentals of electricity markets. But before, let's have, oh, by the way, one heads up. Today we have a good number of slides, so we may go beyond 3 p.m. So just for heads up. Of course, you will have a break of 15 minutes in between. So a recap from previous lecture. So here I put a few keywords that I thought they are important keywords from the previous lecture. So maybe for 2-3 minutes or up to 5 minutes, you can check these keywords. Try to remember what you learned last lecture about these keywords. And maybe you can quickly check with your peer, with your friend sitting next to you, what you learned. And then after 5 minutes, we will continue with this lecture. You managed to remember these keywords. We talked about centralized power system versus electricity markets. We talked about supply and demand curves. Supply curve is non-decreasing. Demand curve is non-increasing. That we discussed about merit order principle. It means that we rank generators from the cheapest to most expensive, and opposite for demands. We discussed about finding the intersection, and we refer it to as market clearing, the intersection of demand and supply curve. And we talked why their intersection clears the market under uniform pricing. We discussed about the concept of social welfare and the fact that in the equilibrium point, meaning at the intersection of demand and supply curves, the social welfare is maximum. And we discussed that social welfare is the area region between demand curve and supply curve. We talked about equilibrium concepts, meaning that at the equilibrium point, the price for that is the market clearing price under uniform scheme, and also all the generators and demands. In the left-hand side of the equilibrium point, they have the accepted bids and offers, while others in the right-hand side, they don't have any accepted bids or offers because they are either willing to sell electricity at a very high price, or from demand side, they are wishing to buy power at low price. We talked about pricing mechanisms, uniform pricing versus pay as bid. So pay as bid simply means that what you bid or what you offer, you will be paid or charged at that price, while in uniform there is a single price for everyone. So it doesn't matter at what price you offer or bid. If you have accepted bid, you will be paid or charged at the same price. And we also discussed how electricity markets are unique in terms of having underlying physics, Kirchhoff laws about demand elasticity, and also about the fact that electricity is not a storable commodity at large scale. So let's move on. So as I said, we discussed that, okay, conventional generators, renewables, they submit offer. Offer means a package of quantity and offer prices. Then demands, they submit their bids, which is a package of their bid price and quantity. So it goes to market clearing algorithm. The market clearing finds the supply and demand curves. Remember those curves from Nord Pool. And then the intersection is the market price. And then we discussed that we will see it's not easy all the times to do it manually just by curves. That's why we are going to drive optimization problems for this gray box today. And the outcomes of this market clearing algorithm will be clearing price under uniform pricing scheme and also the quantities to be traded from both demand side and supply side. Good. I forgot to mention you last time. So if you're also, in addition to all books I introduced to you, if you are looking for one extra also teaching learning material, my colleague Pierre Pinson, who used to be at DTU and who used to teach this course, he also uploaded his very nice videos on YouTube. They are public videos, and also you can watch that. So I took over this course from him 4 or 5 years ago, something like that. Good. Learning objectives of the lecture today. There are 4 things we like to learn today, and you will be tested by Kahoot quiz at the end. One is that we are going to learn about various market actors. Then we are going to learn about different electricity markets. Then we will talk about European versus US electricity markets. Why I'm talking only about these 2 geographical areas? Well, of course, there are also other electricity markets in other parts of the world, in Australia, in Canada, in South America, in China, and etc. But usually, one of these 2 concepts or types of electricity markets also have been adopted in other parts of the world. So I'm not excluding electricity markets, in other side of the world. No, usually they take one of these 2 styles. But also there are some exceptions. For example, in Australia, it's a kind of different type of market. I'll talk about that when the time is right. And then the 4th learning objective of today, it will be a bit of mathematical aspects, how we can write optimization problem, how we can derive this optimization problem, and what this optimization problem does. Good. So let's start with various market actors. Good. So when I say market actors, also it can be referred to as market players or market participants. So when you see that I'm using these words interchangeably, I'm all talking about the same thing. So far, which market actors have we identified so far in the previous lecture? Can you remind me? Yes, please.
Yeah, so it's power producers and demands.
Power producers, exactly, and power demands. They are building the demand and supply curves. Very good.
And also the market operator.
Market operator, remember, it's a non-profit third party who does this, clearing, finding the intersection. Very good. Any other market actor you may think of? Let me see if there's anyone else. I don't see anyone raising hand. Yeah, please. Yes, please. TSO. TSO, it's a very, if you stay in this carrier, TSO is a word that maybe you will hear it every day, right? So I don't like abbreviations in general, but TSO is not one of them. So TSO stands for Transmission System Operator. Very good. Very good. Do you know any other actor? Yes?
DSO.
DSO. It's another acronym that hopefully you will like it. because you will use it in your kind of daily basis, depending what position, what job you will take. Distribution system operator. Okay, let's talk about them together. Yeah, as you said, power producers is one of them. When we talk about power producers, it could be a conventional generator. For example, a gas-fired power plant or coal-based, coal-fired power plant or nuclear or CHP, combined heat and power. Did you recognize a CHP plant at DTU campus next to Neto? It's a CHP, right? It produces both power and heat, combined heat and power. Or a power producer could be a renewable power unit. The power comes from wind or solar or hydro or biomass, etc. And a producer, when we talk about producer, we are not talking about owner of a single asset. It could be a producer who owns a portfolio of different types of technologies. For example, think of a producer who owns, I don't know, different types of conventional generators and some renewables on top. Okay? And some examples of producers in Denmark is Arstel, Huffer also, they have mostly CHPs. They are active in both heat market and power. Vattenfall, CIP, Copenhagen Infrastructure Partners, European Energy, they are also developers of hydrogen, European Energy. But you can easily extend this list with many number of companies. Good. Then power demands. Who are buying power from electricity markets? Well, when we talk about power demands, we are talking about large-scale power demands. Otherwise, us with the residential households, we don't participate every day in the electricity. Are you submitting bids every day to the electricity market? No. So someone else is doing that for us. So if you are a large consumer, if, for example, you have a big industrial plant, like, I don't know, for steel plant or aluminum plant or something like that, then you are a big consumer and you may want to participate in the electricity market directly. Or the other power demands, the common one is retailers. Retailers. Have you heard of this word before? Power retailers. What does it mean? Do you know what retailers mean? What's their business model? What is the, yeah, please. They resell the electricity. So it means that they buy from somewhere and resell it. They buy it from electricity markets and sell it to who?
To consumers such as us.
To us. That's true. So a retailer is an intermediate market actor, a middle person, if you want, who purchases electricity in bulk from electricity markets and sell it to a large number of small-scale consumers, like households. So examples of retailers in Denmark are Andel, Evi, Oku, Winstall, and others. So in this website, elpris.dk, you can insert your postal code and then see what retailers are available for you. And sometimes even one retailer offers different type of contracts to you. For example, one contract that you see prices as in the spot price, day-ahead price. Or there might be other contract that offers you the flat price. So then from there you can choose your retailer and you can choose what kind of contract you want to have. Is it clear? So have you checked this website before? Oh, you did. Oh, very good. So whatever you see in that website, there are retailers. Then market operators, we talked, a non-profit entity that receives, that collects all offers from producers, all bids from demands, and then clear the market with the aim of maximizing social welfare. And then after clearing the market operator disseminates the market outcomes to everyone. And examples of market operators in Europe are Nord Pool, Apex, EEX, and there are many. We will talk about them in next lecture. So do we need any other actor? And you already answered the question. Why do we need other actors? Because the market clearing outcomes are eventually our financial contracts. So when you buy or sell electricity in market, you are not necessarily delivering power, receiving power, or producing power at that time. They are like a financial contracts for the next day, or for the next week, or for the next year, right? But we need someone else who is responsible for operating the grid in practice, making sure that, okay, the financial contracts that we have, they are possible, they are feasible, and operate the system. Eventually, we have to make sure that all physics law, they are there, and we operate the system properly. For that, we need TSO, Transmission System Operator. And the TSOs are responsible for the safe and reliable operation of the underlying power grid. Which grid? We are only talking about high voltage transmission level. And usually, the transmission network in that high voltage level, they have a meshed topology. There are loops. So the job of a TSO is to ensure supply security, real-time power supply, demand balance, and system stability. When we talk about system stability, I don't know if you had any power system course, pure power system course, but can you remind me some stability, types of stability that we have to take care of in power systems? Pardon me? Yeah. Yes. So balance, and there should be a balance between supply and demand. If it's not, what will be violated? Frequency. So here we are talking about frequency stability. Frequency stability is one of the things that TSO should take care of. Any other type of stability concerns or considerations?
Thermal limits in the land.
Thermal limits, yeah, of course. But there are the constraints. But have you heard of any other types of stability, like frequency stability? Voltage stability. Well, if you take a very pure power system courses, you will see that there are many stability concerns in the dynamic level of power systems. So maybe you can take power system dynamics course. You can learn about frequency stability, voltage stability, small signal stability, and so forth, right? There are more concerns than just making sure there is a balance. There are more concerns than just making sure thermal limits are fine. No, there are more problems that TSOs should take care of. And in Denmark, Energinet is the TSO. And it has a very special case because it's TSO for both power and gas, natural gas. So the gas network in Denmark is also being operated by Energinet. Energinet publishes a lot of interesting data. So if you're looking for a lot of interesting data, Energinet is kindly producing or providing a lot of data, some of them real-time data of the grid. So you can go to this website and see. Energinet is not the only European TSO that they are very good in sharing data. There are also others, for example, the Finnish TSO, Fingrid, and the Belgian TSO, Elia. Usually I and my students, we use a lot also the data that we gather from their websites, including also Energinet. Good. So as I said, the Danish TSO is Energinet. But who are the other European TSOs? I think we talked a bit about that in the last lecture. So usually every country has its own national TSO, But there are also some exceptions like Germany that has more than one TSO. There are 4 TSOs in Germany. So you can see all the TSOs here in the European level. There is also one entity called ENZOE, a European network for transmission system operators for electricity. And it's based in Brussels. Do you know why do we need ENZOE? So every country has one or multiple TSOs. And now in the European level, we have ENZOE. What's the main role of ENZOE? Yes?
Is it for trading between countries, like the balancing?
ENZOE is a TSO, right? Yeah, you're correct. But ENZOE is not going to be a for-profit entity. Still, it's a TSO, but in European level, yeah?
It's because of the synchronization system?
Yes, correct. It's more about coordination, because we have a synchronous European grid, and then the TSOs, they need to coordinate. And who coordinates TSO? It's ENZOE. Also, there is the same entity for gas. So instead of E at the end, it's G. It's called ENZOG. Okay. But this was in the European context. In the US context, there is nothing called TSO. Usually it's called ISO, Independent System Operator, if there is a market. And if in the area there is no market, usually it's called RTO, Regional Transmission Organization. So here you can see different ISOs and RTOs in US. I mean, among others, the famous ISOs in US are CAISO, the ISO in California, PJM, the ISO in Maryland, Pennsylvania, and New Jersey. MISO, ISO in Midwest. I don't know, ERCOT, ISO in Texas. And usually ERCOT is a very interesting case because usually they have different regulations, policies, operation schemes than other ISOs. Good. And then you mentioned about distribution system operator, DSO. What's the difference of TSO and DSO? TSO is responsible for the safe, reliable operation at what level? High voltage transmission level, where the topology of the grid is meshed. While DSO is responsible for mid or low voltage distribution level, where usually the topology of the grid is radial, not meshed. So examples in Denmark, there are, I think, around 10 DSOs in Denmark, but some examples are Kazempour, Radius, N1, and Sirius. And then every DSO has its own, let's say, territory, region, that they operate the distribution grid in that area. For example, in Zealand, the island that we are there now, you can see that how the geography or operating area of Radius and Sirius, they are separated. So all other DSOs in Denmark, they are operating in Jutland. So just to give you an idea, it's not very market-related slide, but just to give you an idea what DSOs do. For example, this is the transformer loading data of Radius, the DSO in Copenhagen. You can check in this website. For example, they show here. This is the data from my place, and you can, for example, insert your address and see what is the transformer loading in your neighborhood. For example, you can see that in my area, the data are in daily. The dark blue is peak loading of the transformer, while the light blue is average. And for example, you see that a few days back in January 2025, the transformer loading was around 93%. So it means that we are pretty close to congestion, right? So either DSO should expand the grid or increase the capacity of the transformer, which comes with a sometimes huge cost, or we might find innovative ideas how flexible resources like EVs, heat pumps in that area, they can provide flexibility services when DSO has problem. Because you see that there are only a few times that transformer load is very high. We don't need to have it, to increase the capacity of transformer to be used all hours, all days. So maybe you, as talented, brilliant minds, you can find solutions how we can postpone the need for increasing the capacity of the transformer. So this is a typical problems of DSO. I just wanted to give you, a taste of what DSOs they do. Then remember, TSO in Denmark is Energinet, but we have multiple DSOs, and they are connected in a transformer that connects transmission system to the distribution grid, right? So you can think of, I will not go deep, but there are many reasons why TSO and multiple DSOs, they should have a proper coordination mechanism. Of course, they are different entities, but their worlds are not separate. They have to work together to make sure that the entire power grid is working safely. Good. The next market actor that I like to tell you is a market regulator. The market regulator is the entity that supervises, monitors the market performance, and when the market regulator sees that something is not working good, then they have the right to change the policies. Also, for example, if market operators or TSOs, they want to change something, they have to get approval of the market regulator. So in Denmark, the market regulator is the Danish Utility Regulator. In the US, it's FERC, Federal Energy Regulatory Commission. And again, like NZOE at the European level, there is an entity, like a union of regulators, that coordinate the national regulators. And the name for that entity is ACER, which is located in Ljubljana in Slovenia. Good. There are also other market actors, like traders. Have you heard of traders? Now, it's a very popular business in Denmark. And traders could be physical or purely financial. Physical means that they have asset like a battery. So they buy power in 1 hour and sell it in the other hour. But they have a physical asset. Or it could be purely financial. They don't have any asset. For example, they buy in the day-ahead market and sell it in intraday market. What are they? I can talk it in some minutes. Do you know which city now has multiple trading companies in Denmark? And they are growing fast? No. O's. They have Dansk Commodities, N Commodities, and others. But also there are multiple Centrica. And there are also multiple small-scale, let's say, traders today in Copenhagen. So it becomes a very popular business. Yes?
What is the difference between retailers and traders?
Yeah, retailers are buying from the power market and sell it to us. It's also a trader, but a specific type of trader. But here the traders, maybe they are not dealing with small-scale consumers, no. They are buying from market and selling them in the market. So middle person between two markets, not between market and consumers. Is it clear? Okay, then there are other also actors like BRPs, Balancing Responsible Parties, Flexibility Aggregators, and others. I'll talk about them in time, not today. Good. So a recap of actors we talked: power producers, demands, market operator, system operators, TSO, DSO, and in US, ISO or RTO, market regulators, traders, BRPs, flexibility aggregators. They are, you can see it as a list of potential or different market actors. Yeah. Some of them we discussed, some of them not yet. Good. Any questions so far? Yes.
What would, for example, the Danish Energy Agency be?
Yeah, Danish Energy Agency or Energistyrelsen, it's not the regulator by law, but also they are helping a lot in analyzing, designing policies, whatever, all the studies. But at the end, for the approval, it's the Danish regulatory who should do that. So most of the times, if I'm not wrong, Danish Energy Agency, they get jobs, tasks to be done, and it's the regulator who gives this task for Danish Energy Agency to do that task. It's a bigger entity than the regulator. Good, I hope I'm right. I'm 90% confident. Okay, yes.
Can a power producer be a retailer?
Can power producers be retailer? Do you have an answer for that? Can an entity be producer and at the same time retailer? Yes.
Yes.
Yes, they can, but there's a but.
By Danish law, it's not possible.
It's not possible? Yes. So what they do is that they can be in the same big umbrella or whatever of the company, but different offices. They should not talk to each other. For example, retailer and DSOs. Also, they might be sitting in the same building, but two different sides of the corridor. Clear? There should not be conflict of interest. There should not be, you gain some extra, let's say, power because you have also another rule. It's not possible. Good. Very good question. Various types of electricity markets. So in general, I categorize electricity markets in three categories based on what you trade. Based on what you trade. Capacity markets, energy markets, ancillary service markets. So let me get first your, first idea. Capacity market, it means we are trading capacity. So what is the unit of the commodity we are trading? What is the unit of capacity? What? Megawatt or megawatt hour? Megawatt capacity. Very good. Energy market, what are we trading? Megawatt hour energy. Ancillary services, well, yeah, you may not know it yet. Again, it's a capacity, but for different reasons of capacity. It's again megawatt. Okay, let's start with with capacity markets. So capacity markets are designed to ensure that sufficient generation capacity, measured in megawatt, is available to maintain supply security and support reliable system operation. A bit more description. Any producer who is submitting an offer to the market, regardless of whether it will be accepted or not, they are eligible for compensation based on their availability in terms of euro per megawatt. So it means that, for example, imagine you are a gas-fired power plant and very expensive. Remember last lecture we checked the Nord Pool website for aggregated demand and supply. There were some supply, in the supply side, there were some generators offering at very, very high prices. And you can imagine most of the times their offer was not accepted in the market, right? And usually they are gas-fired power plants or some plants that we need them only in very extreme situations. If we let them alone, hypothetically, for example, they are out of the market 95% of the times. Only they are producing maybe 5% of the times. What will happen to them if we don't support them? They will be phased off. There is no business model for them. Yes, okay, 5% or 2% of the times the price is very high. They will earn a lot. But what about the other 97 or 98% of the times? They don't have any. But, okay, who cares? We can let them go. But shall we? It's a free market, right? They are not competitive. Okay, they don't have a good business model. They will be phased out. But as a system operator who wants to make sure system is safe, do we want them? Yeah. But there might be extreme situations that we need them. Or maybe they are extremely flexible units. They can provide us ancillary services, for example. So maybe there are some reasons that we need them. Then this capacity market mechanism exists. In some markets, there's a market for that. In some countries, no, it's just fixed compensation. We pay everyone in the production side, in the supply side, no matter what their offer price is, we pay them. If it's a fixed payment, then it's fixed. Or in some countries, there is a market for that. So by that, we keep them incentivized. We keep them motivated to stay in the market and not to get bankrupt. Is it clear? Good. In Denmark, for example, we don't have a capacity market. But I know that Danish regulatory, they are thinking of starting a capacity market for Denmark. Okay. Let's say we are paying generators. But who is paying that? TSO, okay, TSO or market operator, someone is paying. But they are a non-profit entity. Who's paying eventually? Yeah, eventually it's us. I'll show you. When you check your electricity bill, yes, there is energy consumption cost, but there are also other elements that we are going to talk about that. Okay? Good. Energy markets. So energy market is a central marketplace for exchanging energy in megawatt hour, where electricity supply and demand are matched. But we have various energy markets. We are going to talk about them in this course in terms of, or at different points in time. So this is a time axis. This is the actual time of physical delivery. For example, now or tomorrow or something. The first market, in terms of the chronological order, is futures markets. Have you heard of that? It's the same as share markets, if you want. If you buy shares of different companies. They are long-term financial contracts with a time span of up to 6 years. For example, you can go, okay, where you can buy it, for example, in Nordics, you can buy it in NASDAQ. You can go NASDAQ where you buy shares. You can also go and buy future in future markets for power. For example, you say that, okay, I want to buy 1 megawatt power for the span of the first 6 months of 2026 at price X. Then your offer either will be accepted or rejected. But you are allowed to do that. So you buy power for a specific time period. That time period could be 6 months, a year, 2 years, 6 years, whatever. It's purely financial contract. And of course, you can buy, and maybe tomorrow you want to sell it back. Or you may want to buy more. Clear? What is the purpose? It's price hedging and risk management for buyers and sellers. Imagine you have a steel plant. You can't go every day to day at market and say, oh, oops, sorry. The price was tough. My bid was not accepted. So we have to shut down the steel process for tomorrow because, no. You have to do risk management. You put a good portion of your electricity demand buying from futures market. Or something that it's not market, but I didn't put it here, or you can buy it in a bilateral contracts. You can go directly to a producer saying that I want to buy from you at this price. There is no market anymore. Two-side agreement. Is it clear? We will not talk about this market, by the way, in this course, because there are many other things to cover in other markets. But it's also very important. And especially if you like to have more competences like a financial engineers, it's a market that you can focus on. For example, many traders, I said, they buy here and then they sell it in the same market or other markets that I'm explaining now. Clear? Then we have something called day-ahead market. Day-ahead market. Maybe it's the most well-known market because most of the volume of electricity are being traded there. It's the main marketplace. Also, it's known as a spot market. So day-ahead market or spot market, they are the same things. So in the case of Nord Pool, in the case of Nordic countries, what happens is that this is time. This is, for example, tomorrow, day D. And D minus 1. This is why we call it day ahead, a day before. Until noon, 12 p.m., if you are a generator or demand or whatever, you submit your bids and offers. And then exactly sharp at noon of day before, the market is closed. Then Nord Pool or any other market operator starts clearing the market, finding the intersections. And until 2 p.m., they clear the market, and up to 2 p.m., even sometimes earlier, they announce market clearing outcomes. So maybe if you can check the Nord Pool website, you can see that the market prices for tomorrow are out. But until 2 p.m., definitely they will be out. Is it clear? So we buy and sell power a day before for every hour of the next day. That's why we call it day ahead. So in Nord Pool, it's also called Nord Pool L-spot, electricity spot. So we buy it a day before noon for every hour of the next day from midnight to midnight. Clear? Very good. I have one lecture. Next lecture will be only dedicated to day-ahead market. So there are a lot of details that I will teach. Just now, I like to give you a high-level picture. Yes?
What's the smallest time span you can buy energy for?
It's 1 hour. 1 hour resolution. So if you bid there, it should be for 1 hour, either for buying or selling. There are some ideas in Nord Pool to make it 15 minutes. It will happen, but maybe not very soon. Right? Yes?
Do it because they don't really know when I am going to consume energy. Do they just guess a medium amount because
that's why retailer profit maximization problem. It's very interesting. It's a decision making under uncertainty. Did you take course decision making under uncertainty? Stochastic optimization is a big thing in electricity markets. I'm not going to. Okay, in the second part of the course, we are going to talk a bit about stochastic optimization. So there are many problems that you have to make decisions under uncertainty. You don't know what will happen tomorrow. You don't know when I will consume power tomorrow. You don't know what the price will be tomorrow, right? So that's why it's also mathematically interesting to work in this area. Okay. Sorry that I can't provide you more detailed answers than. It's a field. You can write a PhD in that. Good. Then there is a next market called intraday market. Intraday market. Have you heard of that before? So intraday market in Nord Pool starts from 3 p.m. 3 p.m. of D minus 1. And it goes until 1 hour before the time delivery. For example, if you are talking about 10 p.m. tomorrow, it goes from 3 p.m. to 9 p.m. of 3 p.m. of D minus 1 until 9 p.m. of day D. It's intraday market. Why? Sometimes, of course, you traded electricity in day-ahead market, but now there are some reasons that you want to modify it. Maybe you have updated forecast of your wind. Or if you are a retailer, maybe you have an updated forecast of how much demand you will have tomorrow. Or maybe you realize one of your assets are out for tomorrow. You just realize it after day-ahead market clearing. Or maybe you are a trader. You want to buy and sell and earn money. Then you go intraday market. Is it clear why do we have intraday market? Then you don't need to leave these changes to be happen in real time. Again, there will be a lecture that I'll only talk about intraday market. Just for now, you should know that intraday markets in Nord Pool, they used to be only continuous markets. What is continuous market? It means that there is no gate closure. Day-ahead market, you say, 12 noon, done, I don't accept any more bids and offers. But continuous market, no. All the time, bids and offers, they can come. For example, I don't know, Raul, right? You tell me that I want to buy 5 megawatt power for tomorrow from 3 p.m. to 4 p.m. at price X. And I see that, and I say right away, Raul, I like it. You send it somewhere in Nord Pool that we call it order books. I see it and say, Raul, I like it. I hit your offer. So then I buy it. You can do it continuously. There is no gate closure. There is no market clearing. I'll talk about this more in 3 lectures from today. Also now Nord Pool has discrete auction-based markets for intraday. It's in a European level. I'm going to talk it later in the 3rd lecture from today. Then the last market that I will talk is balancing market. So it's also called as imbalanced market or real-time market. And it's a market that we clear very close to real time. Remember, intraday market, we finish it in 1 hour before the real time. Then just to make sure that if still there is some adjustment, some imbalances between supply and demand, then we can buy or regulation services to make sure that there is a supply-demand balance. So it's a balancing market. Again, there is a dedicated lecture for that. So this is the last slide before the break. Ancillary service markets. Again, we buy capacity, but only for balancing purposes. Imagine that we are pretty close to real time and we realize, we need 2 megawatt. We have 2 megawatt supply deficit. So someone should increase its production by 2 megawatt. You know it just 5 minutes before the real time. Can you just put the system under risk and say, okay, hopefully there will be someone who would increase its production by 2 megawatt in 5 minutes? No. You have to book some people, some assets from a day before saying that be there. If I need any balancing services, I will activate you. And we call it ancillary services. So there are different types of services: primary, secondary, tertiary reserves, black start, reactive. Again, there will be 2 lectures. I'll talk about that. Only ancillary service markets. Again, there are many companies, even startups, that their business model are based on ancillary service markets. It's very important things. I told you 2 important acronyms, right? TSO, DSO. There are 3 more, but you don't need to remember them today, but we will talk about that later. FCR, AFRR, MFRR. There are different frequency services. We are going to talk about them in this course, but not today. Even I don't tell you today what this abbreviation stands for, though you can Google it, of course. So we talked about different markets. Capacity market for availability, and we said we are not going to talk about that. Then for energy markets, we talked about futures markets. Again, this course will not cover it. But all the markets now I'm saying, I would like to put them in this slide to see when we clear it and who clears it. It's day-ahead market, intraday market, balancing market, and reserve market. So let's see how, so all of them, they are short-term markets. Short-term means in contrast to futures, they are being cleared a day before or in the same day. Let's see how we can see them together. Day-ahead market and intraday markets, they are blue boxes, means they are being cleared by the market operator. For example, Nord Pool, Apex, others. Remember we said day-ahead market, you can bid your offer, you can submit your bid or offer until noon of day before, and then the market outcomes will be published by Nord Pool by 2 p.m. T-1. Then you can go intraday market as buyer or seller to modify your day-ahead position. It goes from 3 p.m. until in Nord Pool, until 1 hour before the time of delivery. These two markets are being cleared by Nord Pool. So it means that at the end of intraday market, you have a position, you have a financial position of your day ahead, then may be modified in intraday. For example, you sold 5 megawatt in day ahead, and then act as a buyer for that hour in intraday with 2 megawatt. So 5 minus 2, 3 megawatt. You are supposed to produce 3 megawatt. Is it clear? Or you are a wind farm, you sold 5 megawatt in day ahead, then later you realized based on your updated forecast, no, you can produce more. Then you also placed 1 megawatt of selling power in intraday. So 5 plus 1, 6 megawatt. Your final position is 6 megawatt. So now we have to see if we can operate the system with this financial contracts or not. That's why now we sent the ball to the hand of system operator. So that's how market operator and system operator in Europe, we can differentiate them. So we have a balancing market in real time. Who clears that? System operator. So balancing market and ancillary service or reserve markets, they are being cleared by system operator, in Denmark by Energinet. They are in green. So what is the balancing market? Okay, as a wind farm, you are supposed to produce 6 megawatt. But something happens. Your forecast was very off, but you're only producing 4 megawatt. Your financial position is 6 megawatt, but you are in practice producing 4 megawatt. System has a deficit of 2 megawatt. It means as a wind farm, you are causing imbalance. How to take care of that? TSO takes care of that in the balancing market. So there is a market to find another resource to produce extra 2 megawatt. And this balancing market pays the one who provides balancing services, 2 megawatt, and penalize the wind farm for causing 2 megawatt imbalance. Is it clear? But as I said, balancing market happens in real time, almost real time. You cannot just pray that, okay, hopefully there will be someone who offset the 2 megawatt imbalance. We have to make sure that we already booked flexible resources, either in generation side or demand side, to provide us balancing services. We call it ancillary service markets or reserve markets. Who clears that? Again, TSO. When? A day before. In Europe, before day-ahead market. So day-ahead market is being cleared at noon, T-1, but reserve is even before. So as a generator, flexible generator, in short term, the first market you can bid is ancillary service markets. Then day-ahead market. Then intraday. Then balancing. Is it clear? And when I say reserve, I don't want to go deep today, but you will see in lecture 6 and 7, we are talking about different types of reserves. It's not just one market. So you can see that there are multiple boxes, not just one box there. Is it clear? So far just I'm trying to give you a big picture, right? So next lecture, lecture 3, will be exclusively on day-ahead market. Lecture 4 will be on something else, equilibrium versus optimization. Lecture 5 will be exclusively on intraday and balancing markets. And then lecture 6 and maybe 7 will be exclusively on reserve markets. So as you see, I'm just providing you high-level information today. I know you have a lot of detailed questions. I think I will address them in the corresponding lectures. Clear? So far, system operator, market operator. Different markets they take care of. Yes?
You said that Nord clears the market based on bids and offers, but the TSO clears the reserve markets based on forecasts, or they do get bids and offers also?
Yes, we will talk about that in lecture 6 and 7. There are a lot of challenges, I can tell you. Yeah, good point. So, maybe a bit of teaser. So if you follow Energinet these days, they are very proud of something called dynamic dimensioning. I will tell you in lecture 6. A day before, they forecast how much reserves they need, and then they buy based on their forecast. Before it was static, now it's called dynamic dimensioning. And yeah, it's very interesting, I guess. Again, PhD, that's the topic. European versus US markets. Yes?
Does the inclusion of capacity market affect the price that is used in the day-ahead market or the lithium market?
Which capacity market you mean? I mean, for long-term purposes?
The capacity market you talked before the break.
Yeah, the one that we don't cover. It goes, okay, country by country it might be different, but it's based on what you offer in day-ahead and intraday markets. If you are available, just for your availability, you get a compensation.
So the markets are not separate?
There is a separate market. Oh, sorry, now I got your question. For capacity services, we have a market. I'm not talking about ancillary services. Then there is a different market. And usually it's long-term.
Will that market affect the price?
Of course. All markets affect each other, right? Yes. Good. I don't want to deviate towards capacity markets, right? Good. European versus US electricity markets. Do you know any difference, fundamental difference between European-style electricity market and US-style electricity markets? Yes. Frequency what? Frequency of the grid. Yes, of course. In Europe it's 50 hertz, in US it's 60 hertz, but it's not market. Market, I'm talking about market differences. Yes?
In Europe there is a zonal representation of the system, where like in US it's
Yes. So for example, again it will be something to be discussed further next lecture, but say for example we have a network of 6 nodes, for example. Each of them, it's a transmission bus bar. For example, imagine that this is Denmark and this is Sweden. So when you clear market in US, you model every transmission line between 6 nodes. We call it nodal representation of the network. While in Europe, for some historical reasons, we go for zonal. We say that we ignore all lines inside every zone. So we see it as zone Sweden, zone Denmark, and connected by a line. So instead of 6 nodes, you represent the network via 2 zones. Of course, this is simplification. Why do we do that? What are the implications? We are going to learn it in next lecture. Also, task 3 of your assignment is all about that. So why this is happening, if you agree, I like to leave it to the next lecture, because we can talk half an hour about that. But this is nodal representation is the US way, zonal representation is the European way. Good. Any other difference? Yes? No, in US, we have something called IS, or Independent System Operator, like PJM, Kaizo. In Europe, we have TSO. Okay, of course, different names, but do we have different, how to say, tasks for them in US and Europe? Or just the names are different? Okay, let me go. Yes, please, Jalal.
That I remember that the ISO is also a regulator.
No, the regulator in US is FERC. We just mentioned that, right? So there are, I like to mention four differences. This is difference 1 in terms of market and system operation. In Europe, TSO and market operator are different entities. You just signed the previous lecture, right? Previous slide. Nord Pool clears day ahead, and intraday markets, TSO, like in Eginet, they clear reserve markets and balancing markets. 2 different entities. While in US, ISO takes care of everything. It's a single entity. From market to operation. Clear? The second difference is what just we discussed, nodal versus zonal. In Europe, we go for a simple way of representing power grid using something called bidding zones. Bidding zones. While in US, we go for nodal representation. This causes a lot of, this has a lot of implications. Please be patient. We are going to talk about that next lecture. But let's see about the bidding zones in Europe. This is the bidding zones in Europe. Maybe you can check it for 30 seconds and see what kind of configuration you see for bidding zones in different countries. Is there only one bidding zone per country? No. Do you see a particular pattern? No, it's a bit of random, I would say. I would say there are historical reasons behind, so developments or history. So how many bidding zones we have in Denmark? 2, DK1, which is the Jutland area, and DK2. You will see in future, in the next lectures, DK1, Jutland, it's connected to European continental grid, while DK2, here, Copenhagen, is connected to Nordic power grid. There are some implications we are going to talk about when we talk about reserve markets in lecture 6. How many bidding zones in Norway? 5. How many bidding zones in Sweden? 4. Germany, together with Austria, 1. France, 1. A bit teaser for future, next lecture. The immediate implication is, in Denmark, how many prices you may have? 2, if there is congestion. It's a teaser. I'm going to talk deeply about that next lecture. So DK1, DK2 prices might be different. How many prices you may see in Germany? One. Is there any chance that day-ahead price in Hamburg and Munich different? No, because we see the whole Germany as one bidding zone. Is it clear? It's just a teaser, right? Okay. In terms of reserve and energy markets, you just saw that in the previous slides. TSO and EGNET clears reserve markets, while market operator and Nord Pool clears day-ahead market, intraday market. So this is energy markets, reserve markets. But in US, there is only one entity doing everything. So if there's one entity doing everything, do you think, in terms of resource allocation, does it make sense to allocate resources separately or in one market? What's your intuition? For example, your conventional generators are going to provide you reserve and energy. Do you want to, in terms of resource allocation, optimality, do you prefer to buy everything at once, make this decision for everything together simultaneously, or do it one by one? Simultaneously. Always it's good to make decisions simultaneously. Do co-optimization. And in US, they do it because there's only one entity doing everything. While in Europe, it's different. First, TSO clears reserve market, and then Nord Pool or market operators clears energy markets. Clear? The fourth difference and the last difference is a bit complicated. Not complicated. It's about the way generators and demands, they bid. If you have a conventional generator, are you aware of any technical limits this technology may have? For example, you have a coal unit. Have you heard of any technical limit? We call it unit commitment constraints. Are you aware of any limit? For example, if now you are producing 10 megawatt, can you increase it by a magnitude of 10? I don't know, to 100 megawatt until next hour? No, there are thermal limitations, thermodynamic limitations. So conventional generators, usually, they have technical constraints like ramp rates, minimum uptime, minimum downtime. Have you heard of these things? For example, if you are on, you should stay on for at least 5 hours. These are technical constraints. So in Europe, market says, you constrain your problem. So internalize is a keyword. Internalize your constraints into your bids in a way that your offers reflect your internal constraints. Is it clear? So market operator assumes that when you submit a bid, an offer, if it's accepted, you will have no problem in terms of your technical constraints. But on the other hand, well, imagine, for example, we have something, I just mentioned it. For example, for a nuclear power plant, I don't know, or coal, if you turn it on, you have to keep it on for 5 hours. But if you ask this generator to submit day-ahead market hourly bids, then it may happen that we accept bids for this generator for 2 hours, but not the next 3 hours. So what to do? Is it clear what the problem is? So that's why in Nord Pool or in European markets, on top of hourly bids, there is extra type of bids. It's called block orders. I will not provide extra information, but you can go to this webpage of Nord Pool and read. For example, as a conventional generator, you are allowed to say that I'm producing, my bid is from 2 p.m. to 6 p.m. for 4 hours at the price of at the bid offer price of, I don't know, for example, 10 euro per megawatt hour. And then it comes as a block. It means that market operator either accepts it as a whole or rejects it as a whole. Is it clear? This is the most simplistic way of block orders. For example, it could be something like this. It's three steps, but again, it's a package. Either market operator accepts everything or declines the whole bid. Okay? So why do we do that? Why Nord Pool or other market operators in Europe allow these block orders? Because generators or everyone in the market, they are responsible to internalize their internal constraints in their bids. For example, by this, you make sure that your ramp limit is fulfilled. Clear? So in Europe, usually we say we have complex offers, simple market clearing. In US, it's opposite. In US, we have simple bids, complex market clearing. In US, generators, like conventional generators, they submit their all technical constraints to the ISO, and ISO, when clearing the market, considers all these technical constraints. For example, conventional generators, they submit their ramp limits or minimum uptime limits to the ISO. Is it clear? And then ISO takes care of everything. So then you can think that the market clearing optimization problem in US, it's complicated. It includes all technical constraints of different producers. Clear? Good. So there are the main four differences of markets in US and Europe. Hope this was like a warm start for you to do a bit of math together. Are you ready? Good. Very simple illustrative example. No network. You will not hear about network today, neither zonal nor nodal. Imagine there is a wind power W1, and production forecast is 20 megawatt. There is only, imagine we are only talking about a single hour. We are going to add hour dimension later. So for a given hour, our production forecast, for example, this is a forecast for 2 to 3 p.m. tomorrow, is 20 megawatt. And imagine offer price of this wind farm is 0. Also, we have two conventional generators, G1, G2. G1, capacity 50 megawatt, offer price. And hopefully this offer price, it's the production cost, fuel cost of G1. It's 20 euro per megawatt hour. G2, more capacity, 100 megawatt, but also a bit more expensive, 30 euro per megawatt hour. Imagine your demand is inelastic to price. It means that demand says at any price, I'm willing to buy electricity. So here in our example, demand is inelastic to price. It means it doesn't react to price. So if our inelastic demand is 40 megawatt, so we have merit order. We first put W1 because it's cheaper, then G2, then G2, it's then G1, then G2, which is the more expensive one, the most expensive one. So it's a supply curve. Demand curve is vertical line because it's inelastic. At any price or at price of infinity, demand is willing to buy. How much? 40. So if you are the market operator, what will be the market clearing outcomes? What will be the production level of W1, G1, G2, and what will be the market clearing price? So what is the production level of W1? 20, full schedule. For G1, 20, while the capacity is 50. So it's a partial schedule. And production level of G2? 0. What is the market clearing price? 20. Why did you say 20? Because it's equal to the offer price of the last generator or the marginal producer, the last generator dispatched. Usually, how do we know the price? If you change the demand by epsilon, epsilon means, I don't know, 0.0001 megawatt. But here, say, for simplicity, 1 megawatt. Either increase or decrease it. We are trying to find the right-hand side and left-hand side sensitivity. How much the production cost will change. If you change demand from 40 to 41, how much the production cost of G1 will change? 20. If you reduce demand from 40 to 39, how much the production cost of G1 will change? Again, 20. Right-hand side sensitivity is equal to left-hand side sensitivity. It means the market price here is unique, which is 20 euro per megawatt hour. Is it clear? Good. Is there a question? Good. So let's write, this is the first mathematical model optimization problem that you see. What you did in your head can be done by this optimization problem. Can you check it for a minute and see what it is? Is there anyone who's willing to give the first description of this optimization problem? Yes, please.
We want to minimize the total cost
We want to minimize the total cost
of the expense that we are facing due to our demand.
Okay.
And, on the basis of how much energy we are purchasing for every producer.
Right. Very good. Very good. So this is an optimization problem. Remember, every optimization problem has something as minimizer or maximizer. In this case, it's a minimizer. You list all the decision variables always to do a proper job under the minimization or maximization. For example, x. Then you have something called objective function. For example, f of x. You are minimizing a function of f of x, which depends on your variable x, subject to some equality constraints, and inequality constraints. So equality constraint, inequality constraint, objective function, your variables. And as you see, there is also something in front of your constraints, like lambda and mu, that I'm going to talk about them, what they are. They are dual variables. Good. So here in this case, you are minimizing. You have three variables, PW1, PG1, PG2. What they are? What are they? They are production level of W1, G1, G2. Then your objective function is 0 times PW1 plus 20 times PG1 plus 30 times PG2. What is 0, 20, 30? What are they? They are the offer price of 3 generators. You receive that as input data. Clear? Here you are minimizing. What are you minimizing? Remember, you have a supply, in this case it's 0, you have a supply curve of something like this, but your demand is inelastic. Remember, last lecture I told when we clear the market, what do? We maximize social welfare. But it is the case if demand is elastic. We have bits from demands. Here, we don't. It means that demands are willing, demand is like constant. They are willing to buy electricity at any price. Then social welfare maximization shrinks, reduces to just minimizing the cost. Here, your wind is offering at zero price. If it was not zero, it was something like this, then your production cost is also all this area. So you are trying to minimize the generation cost. That's what your objective function is. Is it clear? Good. Then you have, how many constraints do you have here? How many? You have 7 constraints. The first one, you have upper bound and lower bound. Lower bound 0, upper bound 20. That's why you have 2 dual variables, mu underline and mu bar. What dual variables are, I'm going to talk about that in a minute. So 2 constraints for W1, 2 constraints for G1, 2 constraints for G2. These constraints are inequality constraint and enforcing the power production of the corresponding generator to be between 0 and their capacity. In case of wind, it's forecast. Is it clear? Clear? Good. What is the last constraint? It's equality constraint, forcing balance between total production and generation. So the 3 generations together, they have to supply 40 megawatt of demand. Clear? So, set of primal variables, objective function minimizing total production cost, and set of constraints, including 6 inequalities and 1 equality. That's, we have 7 constraints, and we have 7 dual variables. We usually use mu for dual variable of inequalities, and lambda for dual variable of equality. Okay, when we say dual variable, you can also refer to them as Lagrange multipliers. Every constraint has 1 dual variable. How many of you knows what dual variable is? Did you take any course that you learned about dual variable? I know it's a prerequisite of this course. How many of you knows dual variable? Others? You didn't take prerequisites seriously? Okay. Is there anyone who can tell me mathematically what dual variable means? When we say lambda is the dual variable of this equality constraint, what does it mean? What does it show? Yes?
It's the sensitivity of the objective function if you change parameter.
Very good. Every dual variable shows that if your constraint is changed a bit, for example, instead of 0, you have 0.00001, how much your objective function value in the optimal point will change. Is it clear? The sensitivity of the objective function with respect to any change, a small change in that corresponding constraint. Clear? Very good. Okay, from optimization courses, do we know about the signs of lambda and mu? Do we know it? Lambda is for equality constraint. Do we know about the sign of this? Lambda is free. It means that it can take any real value. It could be positive, negative, 0. Mu is corresponds to inequality constraint. Do we know about its sign? Yes? It's non-negative. Non-negative means it might be either 0 or positive. Okay. Good. So we talked about these constraints. Wow, we like lambda. Why do we like lambda? Because lambda, which is dual variable of power balance constraint, it gives you what? Market clearing price. Can you tell me why? We just talked about the definition of dual variable as sensitivity of objective function with respect to that constraint. Why do you think lambda gives us the market price? Of course, under uniform pricing. Still, we have our figure here, right? Yes, Raul?
How much the total cost changes
Yes.
if you increase
Exactly. Very good. Here in this case, objective function is the total cost, which we said it's this area. And demand is 40, right? If we change 40 to 40.1 or something like that, either in the right-hand side or left-hand side, in any side, by changing demand a bit, lambda shows how much the generation cost changes. That's what price is, right? Price shows how much your objective function changes if we change demand a bit in that node. Here we have only one node. Clear? Good. But how we can drive the lambda, the value for lambda? Okay. You will code in Python, in Julia, and then when you get the result, you can ask Python, Julia, MATLAB, whatever, to give you also the dual variable, optimal dual variable for every constraint. And you can ask Julia, Python, whatever, to also report you dual variable of this specific constraint. You can do that. But if you are interested to derive it manually, how you can do that? So the next 10 minutes will be a bit mathematical. Have you heard of Lagrangian function? How many of you know how to derive Lagrangian function? Oh, man, you didn't take my prerequisite seriously, huh? Or maybe you're shy. I don't know. Okay. Okay. We want to derive Lagrangian function of this optimization problem. How can we do that? Is the color clear, or I have to change the color? Is it okay? Yeah? Yes. Okay, Lagrangian function, which is a function of what? It's a function of primal variable, x, and function of our dual variables, lambda and mu, is equal to. The first thing is that you have to make sure your optimization problem is in the standard canonical form. It means it's minimization. If it's maximization, make it minimization by multiplying the objective function to a minus. Okay? Equality constraint, fine. Inequality constraint should be in the form of inequality. If your inequality is in the form of greater than or equal to, again multiply the both sides by a negative, then your sign will flip. So this is in a canonical standard form. So that's the first thing you should do. Minimization, inequalities in the lower than or equal to form. Lagrangian function is your objective function, f of x, plus dual variable lambda times gx. So make sure this is 0. If you have any constant or whatever, transfer it to the other side. Again, plus mu times h of x. If these are vectors, for example, you have 5 equalities, 10 inequalities, so they are in the vector forms, then you have 10 lambda, I don't know, 10 mu's. Then you write them, all of them, in that way. So I put lambda transpose and mu transpose if you have a vector of them. If there are 1, it's only 1. So this is the Lagrangian function. Clear? So far easy, right? So we have our original optimization. Now we write its Lagrangian function. So we like to solve it by hand, not by Julia. How we can do that? We can write a system of equations that we are going to call it Kirsch-Cohen-Tucker KKT conditions. They are optimality conditions. It means that if we solve, if our original problem is convex and also fulfilled some conditions that I'm not going to talk about that here, but we have all these conditions here. If we solve this system of equations, the solution is the solution of the optimization problem. Is it clear? So maybe Julia Python will give you the optimal solution for your optimization, but what you don't see behind the scene is that they solve this system of equations. Clear? So we derive these KKT conditions, a system of equations, whose solution gives you the solution of the optimization problem. There are 4 ingredients. What is the first one? You take the derivative of Lagrangian function with respect to every primal variable and put it equal to 0. We learned it in high school, right? I mean, when you drive to find something, the optimal point of something, you derive the derivative and make it equal to 0. What is the second one? It's the original equality. Let me skip the third one. What is the last one? We already said that lambda is free. Now let's talk about the third one that we call it complementary slackness. When we say that j of x is less than or equal to 0, or it's the same that saying j of x minus is greater than or equal, they're equivalent, right? Then remember we said mu is non-negative. We also have it here. Then we have this sign of particular. So this is clear. This is clear. But maybe this is not clear to you. What does it enforce? It simply informs mu times j of x, either with negative or not, equal to 0. It enforces dual variable times the primal variable j of x, the function of primal variables, is equal to 0. It means that either mu is equal to 0, or j of x is equal to 0, or both of them are 0. Clear? Good. So let me get back to our market clearing optimization problem. The red box, it's what we saw it before, right? It's our market clearing problem. The first things we do is that we write it in a standard form. Remember, minimization, and all constraints should be in the form of lower than or equal to. Do you agree that the blue one is equal to the red one? Please check it. And you see that we have 7 constraints. Each comes with a variable, dual variable. Then all the constraints, if they are inequality, it's written in the form of lower than or equal to. And objective function is in the form of minimization. It's in a standard form. Do we agree? Easy peasy, right? So now we derive Lagrangian function. Remember, Lagrangian function is our objective function plus, for inequalities, lambda times j of x. For inequalities, mu times h of x. Please check if we derive Lagrangian function correctly. Could you please check it? So objective function, it's here. Very good. For this first inequality, we say dual variable times the left-hand side. It's minus pw. Now for the second inequality, mu bar mu bar is here, times the left-hand side, Pw1 minus 20. Pw1 minus 20. And it goes the same until the last constraint, lambda, plus lambda, times the left-hand side, 40 minus blah, blah. Do you agree? Is it clear? Now we derive KKTs. Remember, the first ingredient is to take derivative of Lagrangian function with respect to every primal variable. How many primal variables do we have? 3. So with respect to Pw1, with respect to Pg1, with respect to Pg2. Is it clear? Let's take the derivative of this function with respect to Pw1, the production of wind farm W1. Okay, here we take the derivative, only we have 0. So 0 comes here. Then we have Pw1 here. So if we take the derivative, it will be minus mu underline. Minus mu underline. Then we have Pw1 here. The sign is positive. So we are going to only have plus mu bar. Then we don't have Pw1 until here. The sign is negative. We have multiplied to lambda. So it's minus lambda equal to 0. You do the same for production of G1 and G2. Is it easy? Is it clear? Could you please raise your hand? Very good. The fourth one is our original equality constraint. Then we have 6 inequalities, so we have 6 complementary conditions. So for example, we say that mu bar times 20 minus Pw1 is equal to 0. At the same time, we say 20 minus Pw1 is greater than or equal to 0. And also at the same time, we say mu bar is greater than or equal to 0. Is it clear? You can check it also later. The box gives us a system of equations. Do you see any objective function in the red box? No, it's just a system of equations. And we learn in high school that we can solve a system of equations. Here, of course, it's a bit tricky because of the complementary conditions. But if you solve this red box, it's the solution of your optimization problem. And it gives you the solution of both optimal primal variables and optimal dual variables, including lambda, which gives you the price. Good. A bit more math. I don't expect you to solve KKT conditions to drive market, to optimize market. What you will do is that you're going to ask Julia, Python, whatever, to solve optimization problem for you, and you will ask Julia, Python to give you the lambda. But what I ask you is that, for example, Julia will tell you price is 30. How to verify it? I want to teach you how to verify the market price equal to 20 or 30 is correct. I like to teach you how to verify it analytically. Clear? Let's get back to our original problem. Ask Julia or Python, it tells you that the production of G1 is equal to 20 megawatt. Okay? So 20 megawatt, what Julia or Python gives us. Why I'm talking about G1? Because G1 is the marginal producer in this case, the last or the most expensive generator that is dispatched, either partially or fully. So it means that its production is not 0. So from KKT conditions from the previous slides, hopefully you remember, we had these 2 complementarity conditions, both related to G1. The first one says that 50 minus Pg1. So what is the value for Pg1 we derived? 20. 50 minus 20 is 30. So this complementary condition says that 30 times mu bar is equal to 0. What do you learn from that? Mu bar equal to 0. What do you learn from the second one? The production of G120 times by, oh, okay, I forgot mu underline. It's a mu G1 underline times mu underline is equal to 0. What do you learn from it? 50 times something is equal to 0. That something is equal to 0. Okay? There's another KKT condition. Comes from the derivative of Lagrangian function with respect to the production of the marginal producer. That's it. It says 20 plus mu bar minus mu underline minus lambda equal to 0. So we learned that both dual variables are equal to 0. It simply means lambda equal to 20. So you verified analytically by your KKTs that price is indeed 20. Right? Then you can trust to your code. Yes, price is indeed 20. Good. Okay. Now let me give you a bit more challenge. If the demand decreases from 40 to 10, what the price will be? 0. And you can really check the price is 0 by by verifying through KKTs, as we just discussed. What's the case here? What the price will be here? 30. Again, you can check 30 through KKTs. What's the price here? $20. Okay, we have one answer, 20. Who says 20? Almost 30% of the class. Who says something different? So what's your answer? Probability. Okay, so here there is the answer that we don't know. It might be 20, it might be 30. Who says that? Okay, 4 or 5 people. Any other answer? Who says it's 30? 2, 3. What about the rest of class? So remember, we said to derive price, either increase the demand or decrease the demand. If you increase the demand, what the price will be? 30. If you decrease it, what the price? 20. Okay, right-hand side, left-hand side sensitivities, they are not equal. It means we have price multiplicity. Not only 20 and 30, but any price between 20 and 30 could be a price. How to know that? Check KKTs. You will see any value between 20 and 30 admits this to be the solution of KKTs. How often do you think it happens in reality? It doesn't happen much. It's a very rare case, especially if you have network, blah, blah, blah. But it's a good mathematical challenge. So let me now add, what is the difference here? Now we make demand, our single demand, elastic to price. So now demand says that, okay, I can pay only if the market price is not above 40. Now what is the objective function? Not minimization, but maximizing the social welfare. It means if you like to derive KKTs, you have to first make it minimization of minus social welfare. Again, here the price is 20, and you can verify it by KKTs. This verification, it's one part of your assignment. I will talk about your assignment soon. Good. So this is market clearing with price elastic demands. Almost the same as before, but the only difference is that now we have a new variable, consumption of D1. We have a new term in objective function, which is 40 times PD1, which is the area under demand curve, minus the area in supply curve. And objective function now is a maximization. Also, we have the last two constraints change. We have a constraint for demand, whose consumption is between 0 and 40 with two dual variables. And in the balance constraint, we have PD1 as a variable, not 40 as a fixed value anymore. As I said, objective function now is social welfare. So if we write our optimization problem with elastic demands in a generic compact form, it doesn't matter how many generators, how many demands we have, it will look like this. Still, there is no transmission grid. Can you check it for a minute and see if it's correct? Anyone who would like to tell me what are the variables? We have two types of variables, PG with index G, P subscript D with index D. What are they? Production of generator G, consumption of demand D. How many variables do we have? So in your assignment also I will ask you to report number of variables, number of constraints, and computational time. Number of variables is G. This means cardinality, the number of sets in G, plus D. For example, if you have 5 generators, 5 demands, 5 plus 5, you have 10 variables, 10 primal variables. Good. What is the first constraint? Objective function is maximize social welfare. The first term is the area under demand curve. The second curve is the area under generation, supply curve. And the difference is social welfare. The first constraint, how many first constraints do we have? D. If you have 5 demands, then you have 5 constraints. It says that demand consumption lies between 0 and the maximum debit. The same for generators. And the last constraint, how many last constraints do we have? 1. The last constraint is 1. So how many constraints we have in total? It's the number of demands plus the number of generators plus 1. This is the number of constraints you have. And therefore, this is the number of dual variables you have. Clear? Good. So this is the compact form. Good. I like to say 2 more things, and then we have a Kahoot. Yes?
Lower limits and upper
Yes.
limits.
Oh, yes. Thank you for telling that. So 2D plus 2G plus 1. Thank you. So, what is the electricity price in Denmark? Have you checked what is the price you pay in your place? You can check, for example, there are different apps, for example, Elect. This is the prices of my place today, for today. I bought from a retailer with a contract that I like to pay based on spot prices, day-ahead prices. Of course, you can pick different contracts. But this is the prices in my place today, from midnight to midnight. First of all, you see that the price is changing over time. What ingredients do you see here? There are 3 ingredients, red, green, blue. What is the red? Tax. You are in Denmark. What is the blue? That's what you learn in this course, day-ahead price. I asked the retailer to show, to reflect they had price to me. Of course, they put some premium on top because also they have a business model. What is the green one? It's grid price. Also, people, they call it grid fee or grid tariffs or network tariffs, different names. Do you know what it is? We are not gonna talk about that in this course, but what is that? And as you see, it's also time varying. So from midnight to 5 p.m., it's the lowest. In the peak hours, 5 p.m. to 9 p.m., it's the highest. And then the rest of hours, it's in between. What is that? Payment for DSO. Is it the payment only for DSO? We don't care about TSO? Okay, it's the payment for grid. TSO, DSOs, they build a grid, a fantastic grid infrastructure to bring power to your home. You pay for it. So DSOs, TSOs, they use it for grid capacity extension, for ancillary service payment, for capacity market payment, and all costs that TSO and DSOs they have. In Denmark today, we have dynamic tariffs. Dynamic in time, not in place. So it means that everywhere in Copenhagen, the tariffs are the same. So your tariff is the same as my tariff, but it's changing over time. Is it clear? Good. Assignment 1, yes?
For the last hour, you don't have any time.
No, there is. Just I clicked on that, so sorry for the color. I couldn't, I don't know why the app didn't let me to. So I needed to click on one of the hours. So there is colors there. So assignment 1, you have it on DT Alert. Today, if you formed your group, and hopefully you did, you can start working. There are 6 steps. So you can already start working on your case study, building your case study, and you can already start working on step 1. And even if you are fast, you can start working on step 2. But you should wait for the next lecture to start working on step 3 and beyond. Yes?
For the third case study, the link does not work.
I checked and it was working, but I can double check. Okay, I'll check it. Could you please write it in the DTU alert? Then I'll reply with the link. Good. Kahoot. Sorry for being a bit late, but let's see who is going to get extra 1%. Yay. So feel free to decide either you like to have an individual group or a group of 2. Okay, a surprise, we have 17 questions. So, please join. And let me tell TAs that we haven't done yet. Hi. We are now in the Kahoot, so maybe in 10 minutes we finish, okay? Are the others here? Okay. $98 groups so far. $108. And as I said, be ready, 17 questions. Wow, what's happening? The number of groups is increasing than the last lecture. 115, 116. Wow, it will be a tough competition for 1% extra. So if you get it, you really deserve it. Wow, this is an endless, it's 121. I don't know what's happening. Okay. Okay, I like to start. 1, 2, 3. Start. A retailer cool. 117 right answer. Fantastic. Retailer buys power from the market in bulk and sells it back to small consumers. Next question. Oops, not this one. So, yeah. Champion wombat. Second. Very good, 73 correct. Nord Pool, Apex, and EX, they are market operators. In the red one, Energinet is a system operator, not market operator. In yellow, ENZO-E, it's the union of TSOs. And in green, RTE is a French TSO, not a market operator. The goat. Third question. Correct, the yellow one. Majority found the right answer. A TSO operates the high voltage transmission grid. EPFL grows. Oh, fantastic. Next question. The Nordic TSOs are yay, the green one. Fingerit is Finnish TSO, Svenska Kraftnät is Swedish TSO, Statnett is Norwegian, and Energinet is Danish. In red, RTE is French, and Tenet is German-Dutch. In blue, Elia is a Belgian TSO, and red is wrong, and Energinet is only TSO for Denmark. Wow, EPFL Bros is still on top. Question 5. Nord Pool clears blue. The Nord Pool only clears day-ahead and intraday markets. Remember, the balancing and reserve markets are being cleared by TSOs. Willy boy. Question 6. Yes. The right answer is yellow. ENZOE coordinates national TSOs and ACER coordinate national regulators. So majority said blue, which is wrong. Still Willy boy. Question 7. Yay. You cannot choose your DSO. For every geographic area, DSO is certain. It's Radios or, I don't know, N1. What you can choose is your retailer from whom you want to buy power. Still Willy boy, standing number 1. Equation, quiz 8. Very good. The chronological order is first futures, then day ahead, then intraday, then balancing. The majority found right answer. Still Willy boy. Quiz 9. It's a bit tricky question. Very good. Denmark has 2 zones, Norway 5, Sweden 4, Finland, Germany, France, each 1. Very good. Still Willy boy, rank 1. Quiz 10. Very good. The one is correct is the yellow one that says network is simplistically represented in a zonal setup. Red is wrong because energy and reserve markets are not cleared simultaneously but sequentially. Blue is wrong because bids are not simple, it's complex. We have block orders. And green is wrong because power producers, they can bid for all assets in every bidding zone. They don't need to bid for every single asset. Still, Willy boy, number 1. Quiz 11. Very well. The wrong statement is the green one. Remember, ISO clears energy and reserve markets together, jointly. But the rest statements are correct. Very good job, Willy Boy. Quiz 12. Yes, the blue one is correct. The signs are positive. The optimization problem was in the standard 4, so plus, plus. Ah, the answer was here, actually. The blackboard. Willy Boy. And Tommy is the second, close to Willy Boy. Quiz 13. Yay! The answer is here in the blackboard. Very good. Still Willy Boy? 14. Very good. Objective function is maximization, not minimization. And it's area under demand curve minus the area below the supply curve. So red is wrong because it should be maximization, not minimization. Oh, Tommy is now one. Question 15. We just discussed about that. Yes, any price between 30 and 40 can clear the market because the left-hand, right-hand side sensitivities, they are not equal. Tommy first, Willy Boy second, and no. Question 16. Multiple questions. Multiple correct answers might exist. Very good. All of them are correct. Dual variable of equality can be any value, positive, negative, 0. KKT conditions can be used to verify price. KKT conditions can be solved as a system of equations. And complementary slackness is the multiplication of dual and primal variables. Tommy first, and final question. In euro per kilowatt hour, not krona, euro. A bit tricky. Yes, it's the red one. 0.2 to 0.5. And the winner, number 3, Tommy. Second, Paul. Number 1, Willie Boy. Who is or who are the Willie Boys? Online, here? Not here? I can't see. Are you raising your hand? No. Here. Very nice. Can you introduce yourself? Just write your names. Yeah. Willie Boys, please just write your names in the chat box, and I can introduce you to the class. Maybe you can also mention your affiliation. We are Inya and Paul from EPFL. So we have winners from EPFL. Congratulations to them.